Hi everybody, this is Dr. Nigro with a Physics Fundamentals screencast. This is the first screencast in the series that will focus on forces and motion. This particular chat is going to deal with free body force diagrams of single objects. There'll be a later screencast that will look at free body force diagrams when you have a system of objects. All right, so let's get started. Let's start with this term, force. All right, now force is defined as a push or a pull on an object that can lead to some sort of change in its motion. That change could cause it to come to a stop. That change could cause it to start moving or change its velocity in some way. All right, now these forces only lead to these changes in motion if there is some sort of unbalanced force that's acting upon that object. All right, and this net force is directly related to the acceleration of that particular object. So because we've got acceleration involved, which in turn then goes towards velocity, then that means that this force is going to be some sort of vector quantity. All right, it's going to have a magnitude, which is the numerical value, and it's going to have a direction. All right, so when we deal with forces, just like when we deal with acceleration, displacement, or velocity, we're going to need to indicate direction. That can either be through some sort of compass direction, east, west, north, south, left, right, forwards, backwards, up, down. But most often we're going to be using positive and negative signs. All right. When we draw free body force diagrams, we're going to be representing these vector force quantities with arrows. All right. So make sure that you're drawing these vectors as arrows. All right. And we're going to use the length of that arrow to indicate the magnitude. And then the direction we point the arrow will tell whoever's looking at our diagram the direction that force is being applied. All right. So let's talk specifically about what a free body force diagram is. All right, it's an illustration. All right, and it shows all the forces acting upon an object. All right, and those forces can be horizontal, so they can be in the x dimension, or they can be in the y dimension, or you're going to see both depending on what the object is doing. All right, well, what do we use this free body force diagram to do? Most often we use it to determine the net force that is acting upon that particular object, because that net force can give us pieces of information about the motion. All right, so for example, F net might be 0. All right, so when we look at all the forces acting upon a single object and we add them up, everything balances. So F net equaling 0 means we've got balanced forces. And if the forces are balanced, you have two options for your motion. It can be still, all right, so not moving, or it can be moving, but at constant velocity. All right, so no acceleration. All right, so that's what happens when all your forces are balanced. Your F net value will be equal to 0. All right, well, what happens if forces are not balanced? In that case, F net will not be equal to 0. So this is going to be unbalanced forces. All right, and all you have to choose from here is motion. So the object will be moving and with changing velocity. So the object is either speeding up or slowing down, or it could be changing direction. Those are all options. All right. So that's what a free body force diagram is and what it can tell us. All right. So now how do we draw a free body force diagram? All right. Well, it's pretty straightforward. We're going to represent the object and we're going to use arrows to represent the forces, but let's just take a minute to remind ourselves of some of these forces that we're going to be seeing. All right. Oops, sorry. All right. So first, hold on. Let me move this guy. There we go. All right. We could have an applied force, a force that's being applied to the object. We could have gravity pulling down on the object. We could have the normal force, which is the support force between a solid surface and our object. All right. If the object is connected to something, either a ceiling or another object through a string, a rope, a cable, we're going to have some tension. All right. If we have a spring involved, we're going to have a spring force. All right. If we move the object across another solid object, we're going to have friction. If we move the object through a fluid, such as air or liquid, then we're going to have drag, all right, which is in the air, also known as air resistance. All right, so these are just some of the examples of forces that you might need to list in your free body force diagram. They're not all of them, but these are the most common ones that we tend to see. All right, so I'm going to leave these up here just to remind you. All right, now let's talk about the steps to draw our free body force diagram. All right, first, we need to represent the object. All right, I do that simply. I use a box. All right, you could also do a circle, or you could do a dot. I've seen all three. All right, the key is it doesn't need to be fancy. All right, this is not art class. If you are looking at the forces acting upon a person riding a bike, you do not need to draw a person riding a bike. If you're good at drawing, you can, but I tend to just use a box. All right, so first we represent our object with a box. That's what you're going to see me do. All right, second, I read the description and then I draw the vertical forces. All right, so those are going to be my Y forces. All right, and those tend to be things like gravity, tension, the normal force, all right, any kind of thing, but it has to be working in the vertical dimension. All right, once I've drawn those in, then I draw in the horizontal forces. So those are going to be in the X plane. All right, now, can forces be applied at angles? Sure. All right, but when you draw a free body force diagram, everything should be either in the X plane or the Y plane. If you have angled forces, you have to break them into their X and Y components and then put the components into your free body force diagram. Now, we will be dealing with angled forces, but not today. We're going to keep it simple today. All right, once we've drawn in our forces, then we need to look at them. So we're going to check for balance among the forces. All right, now, for forces to be balanced, they have to have the same magnitude but opposing directions. So that means that forces in the Y direction cannot balance forces in the X direction and vice versa. Y forces can balance other Y forces and X forces can balance other X forces. All right, when I find forces that are balanced, I put a hatch mark on them. And I'll show you what that looks like. That's just an indicator that these two forces that have the same hatch mark are equal and opposite of one another. All right. Once I've identified all the forces that are balanced, I check for any unbalanced forces. All right. And those unbalanced forces are going to give us F net. All right, so the net force is going to be determined by finding these unbalanced forces. If you have a particular object and based on the description, everything is balanced around it, F net's going to be 0, so you'll be all set. But if you have unbalanced forces, then you're going to need to use those forces to figure out the direction F net points, and if you have numbers, the numerical value. All right, the direction will be indicated with a sign. All right, so with that in mind, we should define our signs. I'm going to define those up top just so they're here. All right, my positive directions are going to be up and to the right, and my negative directions will be down and to the left. That's consistent with what we've been doing with our other vectors, so we're going to keep that. All right, so before we start drawing some of these free body force diagrams, all right, I just want to mention a handy tip that I use. All right, so when I'm reading a description of an object, I ask myself a series of questions that kind of help me focus on whether things are balanced or not and what F net potentially could be. All right, so the first question I ask once I've read the description, I ask myself, is there motion? All right, after I ask myself that question, depending on the answer, I check and I say, okay, well, is the velocity changing? All right, and then I say, is F net equal to 0? Are those forces balanced? And if not, where is the imbalance? Is it X or is it Y? It doesn't tend to be both. It can, All right, if you have forces that are imbalanced in the x and the y, then you're moving at an angle. All right, we're going to keep it simple again today, so we're not going to have that situation, but it could happen. I don't want you to think it can't. All right, so again, I read the description. I ask myself, is there motion? If there's motion, I ask myself, is there a change in velocity? And from there, is F net equal to 0? Based on that, are the forces balanced? And if the answer is no, then where is the imbalance in the x or the y dimension? All right, so what have we got to start with? We have a student pushing a box across the floor to the left with constant velocity. All right, so there is a key term, constant. All right, if your velocity is constant, that means no changing velocity. All right, so we have motion. The object is moving to the left, but we have constant velocity, so no change in velocity. And what that tells me is that my F net has to equal 0. All right, because remember, if you have an F net of 0, you either aren't moving at all or you are moving but at constant velocity. And if F net is going to be 0, then all of my forces are balanced. All right, so that means it's going to be pretty straightforward to draw my object. All right, so I start by drawing a box to represent my object. I'm going to start with my vertical forces. Now, the description does not mention any vertical motion, so I'm going to assume that the box is staying on the floor, all right, which means we've got a gravitational force pulling down on the box. And because it's sitting on the floor, not flying through the air, it's got an opposing force. This is going to be the normal force, the support force, that must be equal and opposite, balancing that gravitational force. All right, so I'm going to indicate that by putting these two little diagonal hatch marks on my arrow. All right, now the description says we're moving to the left. All right, so that means there is an applied force pointing to the left. All right, and because we're moving at constant velocity, it must be balanced by an equal but opposite force to the right. Now the question is, what is this force? All right, so because we're pushing a box across a floor, there's a friction that is occurring between the floor and the box, and that is what opposes our pushing of the box. So these are equal but opposite, so they get hatch marks, but I'm going to put 2 to indicate they are not equal but opposite to our vertical forces. All right, and then I'm going to talk a little bit about the signs of these different forces. All right, anything to the left is going to be negative, and anything to the right will be positive. Anything up will be positive, and anything down will be negative. All right, now in this case, because F net equals 0, it doesn't really matter, but when we move forward, we might find some unbalanced forces, and we're going to need to know what the signs are. All right, so our next object is a book sitting on the desk. So I asked myself my questions. Is it moving? No. Well, if it's not moving, then it definitely is not changing its velocity. If it's not moving, can F net equal 0? Yes. All right, so F net in this case is going to be equal to 0, and that tells me that I have balanced forces. All right, so I'm going to draw my book, and I'm going to think about the motion. There's no horizontal motion here, so that means no horizontal forces. So that makes things simple, right? But I do have gravity pulling down on the book, and because it's not moving, I must have an equal but opposite force opposing gravity, and that again is going to be our support force or our normal force. Hatch marks to show that they are equal but opposite, and that's all you have to do to show a book sitting on the desk. All right, let's slide down. All right, here we have an apple falling and it's speeding up. All right, so again, I have motion. This time I do have changing velocity. So that tells me that F net does not equal 0 and that I have unbalanced forces. So I'm going to need to use my force diagram to show where those unbalanced forces are. So I start with my apple. All right, it's falling. So the force that's allowing or causing it to fall is going to be gravity, just like we saw when we talked about free fall. All right, now it's speeding up. So what that means is it's accelerating as it falls. So it's falling down. All right, so its direction is negative. And if it's speeding up, its acceleration is also going to be negative. And when we work with Newton's second law, we're going to find that whatever the sign of the acceleration is, your F net is also going to have that same sign. All right, so our gravitational force is our negative force. which means that it has to be greater than our positive force. To get an overall net force that's negative, then I need my positive force to be a little bit smaller than my gravitational force. So I'm going to draw a slightly shorter arrow. All right, and this force is not the normal force because I don't have my apple sitting on something. Instead, it's falling through the air, which is just like a fluid. So I've got particles in there that are rubbing against the apple, so we're going to get some friction. But because it's moving through the fluid, we call it drag. All right, I'm not going to put hatch marks on these two arrows because they are not equal and opposite. Instead, my gravitational force is greater than my drag force, which is why our F net is going to be negative. All right? All right. A person driving their car and slowing down. All right, so let's specify that we're going to drive to the right. We need a direction. And we're going to slow down. All right, so let's start with our motion. We've got it. And we also have change in velocity here. We're slowing down. All right, so that again tells me F net cannot be equal to 0. All right, and somewhere in my diagram, I have to have an unbalanced force. All right, so I start drawing my object. All right, I'm going to start with my vertical forces. So I'm going to have my gravitational force pointed down. Now it says nothing about it floating through the air or moving vertically in any way. So I'm going to go with an equal but opposite normal force again, opposing that gravitational force. And I show that with my equal but opposite hash marks. All right, now we're driving to the right. So that means my applied force is to the right. That's the way that motion is occurring, but we're slowing down. So what that tells me is the force that opposes my applied force has to be greater. All right, in this case, that force is going to be due to friction between my tires and the road or between brake pads and the road. All right, so we're going to have forces that are unbalanced. I have a negative force over here to the left and a positive force over here to the right. All right, and then looking at my arrows, my frictional force is greater than my applied force, so my net force in this case is going to be negative. All right. If I wanted to write out my equation, F net would be equal to the frictional force plus the applied force, the sum of my forces. All right. My frictional force would be negative, my applied force will be positive, and because my frictional force is greater, I'm going to get an overall negative sign for my net force. Okay? All right, so that's how we draw diagrams based on description. All right, let's try another type of problem. All right, using the following free body force diagrams, calculate the net force acting upon the object, then describe the motion, including direction where appropriate. All right, so this is going to be a little bit different. This time we've got the force diagram and we're going to use it to find F net. All right, so I'm going to start by looking at this first one right here. I'm going to look at my vertical forces. I have 5,000 newtons down, 5,000 newtons up. So these guys are equal and opposite. So they are balanced. I then go look at my horizontal forces. I have 50 newtons to the right, 30 newtons to the left. So these are not balanced. All right. So my F net is going to be equal to my positive 50 newtons plus my negative 30 newtons. So 50 newtons plus negative 30 newtons. So the net force that's acting on this car is 20 newtons, and that is a positive value. So if I look at the car, it's facing to the right. All right, so I'm going to say traveling right and increasing in speed. All right, the reason I say increasing is because my F net is positive, which means my acceleration is going to be positive, which means I have to be speeding up if I'm also moving in the positive direction. All right, let's look at our baseball. All right, this time no horizontal forces, just vertical. All right, so I've got 5 newtons down and then 0.3 newtons up. All right, so my positive value is 0.3 newtons and my negative value is 5 newtons. So my net force is going to be equal to 5 newtons. 0.3 newtons plus negative 5 newtons. All right, so my net force is going to be equal to negative 4.7 newtons. All right, now I don't really know the direction of travel here. It's a baseball. It doesn't tell me whether it's going up or down. All right, but I can make some inferences. All right, if it's traveling up, which is a positive direction, but I have a negative F net, then I'm going to be slowing down. All right. If the ball is traveling down, which is a negative direction, with my negative F net, I will be speeding up. Okay. All right. Third one, here we have a guy, he's walking his dog. If we look, our vertical forces, we have 35 newtons up, 35 newtons down, so those are equal and opposite. We look at our horizontal, we have 25 newtons to the left, 25 newtons to the right, so those are also equal but opposite. So in this case, F net equals 0 because all the forces are balanced. All right, now, one option would be for everything to stand still, but the picture makes it look like they're moving. All right, so I'm going to say motion to the left at constant velocity. Okay, because that seems reasonable for what's going on in that picture. All right, last, we've got our graduation cap. So I have 3 newtons up, 1 newton down. Remember, our upward direction is positive. Our downward direction is negative. So in this case, F net is going to be equal to 3 newtons plus negative 1 newton, which means our F net value will be equal to 2 newtons total, and that's positive. All right, now again, we don't know the direction of motion, so similar to our baseball, all right, it depends. All right, so if the object is moving up, which is our positive direction with a positive F net, it will be speeding up. All right, if our object is moving down with our negative direction and our positive F net, it will be slowing. Okay, so that's just an example of when you're given all the values and the diagrams already. All right, last but not least, it's kind of a combo. All right, we've got some information. We're going to draw the diagram, and then we're going to fill in all of the numbers that we can based on the description. All right, if we need to, we can describe that motion as well. All right, so let's start with our first one, a 10-kilogram block at rest on a horizontal surface. All right, so we're at rest. So that first of all tells me that there's no motion. And if there's no motion, then F net has to be equal to 0. So we're going to have balanced values here. All right, so let's draw in our block. All right, we're going to have a gravitational force pulling down on the block. And because F net's 0, we need to have an equal but opposite normal support force pushing up. So these are equal, whoops. Oh, sorry. There we go. Equal but opposite. All right, now numbers. Do we know any numbers? Well, I know that Fg is also the weight of the object, and that Fg is equal to the mass of that object times acceleration due to gravity. All right, we've been using 10 meters per second squared for acceleration due to gravity, so 10 times 10. This value is 100 newtons. So Fg is 100 newtons. All right, well, I also know that the normal force is equal in magnitude, but in a different direction, so it also must be 100 newtons. The difference between the two, this is going to be my positive direction, and this will be my negative. So if I calculated F net, I would say 100 newtons plus negative 100 newtons gives me an F net of 0. All right, for our next one, a 50-kilogram man falls with a parachute that provides 250 newtons of air resistance. All right, so we're going to need to check. We can't tell just based on the description whether we've got balanced forces. So this is where we're going to have to use math and quantitatively decide. All right, so let's draw our guy in his parachute. All right, we've got a force pointed down that is Fg, and then we are told there's some sort of drag. All right, now the drag is 250 newtons worth of force. So we need to figure out what is the value of Fg. All right, so again, we know that Fg is equal to mass times acceleration due to gravity. So we've got a 50-kilogram man, 10 meters per second squared. So we're going to get a gravitational force of 500 newtons. So this is 500 newtons. And remember, the drag is providing a positive force. The gravitational pull is providing a negative force. So let's look at F net. F net is going to be equal to our gravitational force plus our drag force. And again, negative positive, just as a reminder. All right, so when we plug the numerical values in, we're going to have negative 500 newtons plus 250 newtons. So the net force is going to be negative 250 newtons. All right, now it tells me that the guy is falling, which means that the direction of motion is negative. All right, so if I have a negative direction of motion and a negative F net value, all right, that means that I am speeding up as I fall towards the ground. All right, let's try this one. All right, a 500 kilogram airplane moves east with a thrust of 10,000 newtons against a westward headwind that provides 3,000 newtons of drag. All right, so again, we're going to have to do some math to make sure what's going on. So we start with our object. All right, now it doesn't mention that it's moving up or down, so we are going to go with the idea that we've got a gravitational force that is balanced by lift. All right, now lift is not one we talked about very much. I talk about lift in terms of the normal force. When you have an object resting on another solid object, the support force, the normal force, is what keeps those objects from moving through one another. When you're a fluid like air or water, all right, we need a different type of force because we don't have solids, all right? And that's where the lift force comes in. The particles in the air provide that support that counteracts gravity. So we're going to have a lift force here. Whoops. And it is going to be equal and opposite to our gravitational force. Now, I could put in my gravitational value. I have a 500 kilogram airplane, so that means 5,000 newtons of gravitational force, which means lift must also be providing 5,000 newtons of force so that they are equal and opposite. All right, now the airplane is moving to the east. So we're going to draw the applied force to the east. Thrust is an applied force. And this value is 10,000 newtons. Right? The problem tells us that we have a headwind working against that thrust. So this is going to be my drag force of 3,000 newtons. All right. So if we think about signs, our drag force is a negative force where our thrust is a positive force. If the plane were reversed in directions, we would change the signs. All right. Our lift is a positive force and our gravitational force is negative, but they're equal and opposite. So we don't need to consider them when it comes to net force. So the net force is going to be equal to that applied force plus the drag force. All right, so we plug in our values. We've got a positive 10,000 newtons plus a negative 3,000 newtons. So the net force that the plane is working with, sorry about that, net force is going to be equal to a positive 7,000 newtons. All right, so that tells me that the airplane is moving to the east, and because F net is positive and east is a positive direction, it must be speeding up as it moves in that direction. All right, last, we have a 10 kilogram block being pushed at a constant velocity to the right with a force of 50 newtons across a rough surface. All right, so the first thing that caught my eye was the word constant. All right, so if we have a constant velocity, that means that we have a net force equal to 0. Okay, so we're going to start with our block. We'll start with our vertical forces, our gravitational force, and our normal force, and they must be equal and opposite. All right, it tells us that the motion is to the right, so that's going to be our applied force, and that it's equal and opposite to friction. All right, now what about some values? Oh, sorry, let me put my hatch marks in. All right, we have a 10 kilogram block, which tells me that the force due to gravity is 10 times 10 or 100 newtons. And it's got an equal but opposite 100 newton normal force. All right, we're pushing that block with a applied force of 50 newtons, and if we're moving at constant velocity, there must be an equal but opposite 50 newton frictional force working. All right, the frictional force would be negative, the applied force would be positive, which means that our net force horizontally would be 50 plus negative 50, or 0. Our upward normal force would be positive, our downward gravitational force would be negative, so our net force vertically would be 100 plus negative 100, or 0. So the net force is going to be 0. All right, so this object is moving exactly as the description says, to the right at constant velocity. Okay? All right, so those are just some examples of how to draw force diagrams and then how to use them. Okay? A later screencast will look at calculating acceleration and some of our other variables, such as initial velocity, final velocity, time, and change in position. And other videos will look at what happens when we have angled forces, or we have inclined planes, or we have systems of objects that move as one. Okay?